So let's please settle down so we can continue this and then go on, okay? My goal today is to cover inductance, inductors, and the magnetic energy. Can I have your attention, please, everyone?
Yes, sir.
Okay, so we don't have too much time, so let's please continue. Because we have the quiz right after. So, all right. So let me. People have been asking me. We learned a lot, and then where do I start, or how do I know what to do? Well, we learned as far as electromagnetism, 4 equations plus 1, 5. So here they are. We learned Gauss's law for electricity that says E dot dA over a closed area. I'll put closed area. It's an area, so it's technically a double integral. We never really do a double integral. Equals to the charge enclosed over epsilon naught, right? And then there was that Gauss's law for magnetism for B dot dA. And technically also it is a double integral. What was that one? 0. Zero. The net flux, net magnetic flux over closed surface is always 0. An area, integral over an area. So this is Gauss's law for electricity and Gauss's law for magnetic fields or magnetism. And then we learned this law that we have been applying over the last couple of days, over the last week. Notice it's an open surface, right? It's an open surface, not a closed surface. This is called Faraday's law. And B dot dA integral is the magnetic flux, so we just write it as D dt of the magnetic flux. This is Faraday. Faraday's law. And then the last one is ampere. B dot ds U dot that passes through, right? So this law, this is Ampere's law. I will leave some space here. The first 3. This is Gauss's laws and Faraday's law. They're in the final form. They're good. They're complete. This one, there will be some additional term we will add to it before it is completely complete. Okay. So this one we will add something to it. So these are the 4 laws that we have seen. Plus this one. Plus the force. The force, the net force on a charge will be the electric force plus the magnetic force. Electric force is the charge times the electric field. Magnetic force is QB cross. Right? Which one do you use? All of them. All of them are applicable. It just depends on the situation and what you want to calculate. So this is just a summary of what we have learned so far. And I'm going to go back to inductance and inductors. So let's talk about, let's review the solenoid. Solenoid. And go from there. Okay? So here is a solenoid. Very long, right? Solenoids are long. And the current will go around, right? Go around like this. So for example, let me try this one. So the current comes out, it goes in. It comes out, it goes in. So every time it comes out, it goes in. solenoid made of? What are these? Yeah, and they're wires, right? And they're conductors, right? Wires are conductors. And yeah, I'm just mentioning that so we can remember. The length of the solenoid this way, it's very long. In principle, if it's ideal, it would be infinitely long. But a real solenoid would have a length there. And if it's a cross-sectional, if it's a circular or cylindrical solenoid, this would be a radius r. So that's the radius of the solenoid. In this case, the magnetic field will be along the axis of the solenoid, right? Going up. Do we remember that? Yes? Yeah. The magnetic field will be going up in this direction. And it's uniform. And how much was it? Well, the magnetic field in a solenoid, U naught, little n times current, where little n, so capital N is number of loops. Little n will be the number of loops divided by the total loops. The total number of loops divided by the total loops of the solenoid. So it's the number of loops per unit of time. That's what good is. Okay. Any questions up to this point? This should be a repeat, right? So there is a magnetic field going up the solenoid. So consider one loop. So here is a loop, right here. What's the flux through that loop? What would the flux be? Can you write it? Flux through one loop? Yeah, magnetic field times the area. Yeah. Right? The area is like this. Take one loop, and the magnetic field is going up, going through it. So it's the magnetic field times the area. The magnetic field is mu naught n I, and the area is pi r squared. Right there. If it's circular area, it would be pi r squared. Yes, so far it's good. Okay. How many loops do I have in total? N of them. So the total flux will be what? You take the flux through one loop and you multiply it by what? Big N. Yeah. So capital N times the flux on one loop. That's big N, little n, pi r squared. Now, we define the following quantity. Self-inductance. It has the symbol L. And what you do is you just take the total flux and divide by I. Total flux divided by current. So basically, everything in front of the I. That's the self-inductance for a solenoid. Okay? So there is self-inductance for different things, different objects. We would do the torus or a toroid. The section that met me yesterday, we did that. The section that hasn't met me yet, we will do it during discussion tomorrow. So for example, for a solenoid, L for a solenoid, what will it be in this case? Everything, right? Except for the I. So it's going to be U naught, capital N, little n, pi, and r squared. So self-inductance. Now, we can write Faraday's law again, or rewrite it in terms of this inductance. So here is how we do it. E dot ds minus d dt of the magnetic flux, right? The total number of loops.
So that small n is density.
Small n is the number of loops per unit of length. Yeah, loop density. Yeah. So we get minus d L times I. Right? L times I is the flux. So we get finally d dot ds equal to minus L times di. Why are we rewriting it like this? We would have a component called an inductor. So basically, you make a circuit and you attach a solenoid to it. Make the solenoid part of your circuit. It doesn't have to be a solenoid, but an inductor, you can think of it, every time you hear an inductor, you can think of a solenoid. Just like when you hear a capacitor, you think of the parallel plate capacitor, even though we had different shapes, right? We had spherical, cylindrical capacitors, and so on. But the thing that comes to mind, or should come to mind, when we say capacitor, is the simplest, it's the parallel plates. Same thing with inductors, we'll have the solenoid. In fact, the symbol for an inductor in a circuit is, will look like a solenoid. So for example, let's just remember, what is this? That. What is this? What is this?
Capacitor.
Good. Well, here is inductor. And we'll see what it does. So it looks like that, right? Now, I forgot to mention the unit for inductance, or for inductance. Inductor is the object, is the component. Inductance is the quantity. So inductance would be measured in units of flux per current, right? So let me just write down here for units. So for L. Well, the units are going to be flux per current, right? What's flux? Flux is magnetic field times area, so Tesla meters squared per current. Current is amperes, right? Those are the units. Now, who remembers the units of flux? What did we call Tesla meters squared? It's kind of not really necessary, but Gauss is a unit of a magnetic field, similar to Tesla. It was Weber, right? WB, Weber. Per ampere. Ampere is coulomb per second, right? Per ampere. And this has a name, actually. Again, it's probably not necessary, but we would give it a name. So a Henry.
Henry?
Yeah.
Henry?
Yeah, just like the name. Henry. So 1H. And this is different, right? It has an H. You wouldn't mix it with anything else. So, okay. Okay. So that's those are the units here. So we're going to, yeah, there are n-named things. Well, electric flux is not named. to my knowledge. Yeah, it's coulombs, newtons per coulomb times square meters. I don't think, I'm not aware that it has a name, so you can claim it. Okay, so we will now talk about inductors and the energy stored in an inductor. Okay. much energy is stored in the inductor. But before we do that, let's consider an inductor in a circuit and then ask what happens. We're going to apply Faraday's law. What remember is what is this? What's E dot S going from A to B minus?
Oh, that's a potential difference.
Delta B.
Delta V, yeah. It's the potential at B minus the potential at A, right? This is delta V. Delta V. Right, that's the change in potential. Just remember that. Okay? Because we're going to do something right now. So let's consider the following. Let's make a switch here. Let's give it a resistor, and let's make an inductor. And that's the switch. Let's give our different points different names. So let's name this point here A, B, C, D, E. Sounds good? Now, remember, what's an inductor made of? Again, wires. Okay, solenoid, and solenoid has a wire, right? Copper wire. So let's think of it as a perfect conductor. If you have a perfect conductor, what's the electric field in there? Let's say when I close the circuit, what's the electric field here? It'd be zero. The electric field in the conductor is zero, right? It's a perfect. So I'm going to close the circuit and ask what happens. There'll be current. We will worry about the current behavior in a little bit. It's going to be time dependent current. The current will not be just some constant current. It will take some time. It will be some exponential function, which we'll discover later. But for now, there will be a current, and the battery will try to push charges to go this way. As the charges get to the inductor, and they start going around, there will be a magnetic field. And if there is a magnetic field, there will be flux. And there was no magnetic field, now there is a magnetic field, so the flux is changing. So there will be opposition, and so there will be an induced field in the opposite direction to oppose the change. Okay. So the current will not be just a steady current from the beginning. It will grow. It goes from 0 to some fixed number, which will, again, I'll do in a little bit. But for now, I'm going to apply Faraday's law to this circuit.
But at T equals 0 after.
At T equal to 0, the current is actually 0. Yeah. So we will, I will get back to it. So, let's apply Faraday's law to this. So I'm going to write here that E dot ds. What does Faraday's law say? E dot ds equals to minus d flux dt, right? And we said the flux is Li, so L di dt. Right? So that's what I'm going to write on the right side because I have an inductor. So that's what I'm L di. We will get a rule similar to just like resistors, when you cross a resistor in the direction of current. So we'll get a rule starting from here. So once we go through the math, we'll get a rule and then just do it. So E dot ds, but to have the change in potential, I need a minus sign here. So I'm going to multiply both sides by a minus sign. Make sense? Multiply both sides by a minus sign, so I have this. E dot ds is equal to what? Yes, good. So L. Right. So let's do this. Do this integral. What's the integral E dot ds from A to B? We're doing a closed loop, right? So I'm going to start at A and go around the loop and come back to A. What's E dot dA going from A to B? What's the change there? Not E dot dx, sorry. Yeah, minus E dot ds from A to B. I don't want to write 5 different integrals. I'm just going to do it quick here. What's the change in potential going from A to B? E. Yeah, good. Plus E. So just E, sorry. E. Okay? How about here, from B to C? What's E dot ds? E 0, so 0. Okay? What's, so from here to here is 0. Okay? No change. It's a perfect conductor. Good. C to D, what's the change? Yeah, current is, minus what? Yeah, good. Yeah. The change in potential, yeah, minus IR. Got an inductor. What's the electric field in it? Inside the wire. 0. So what's E dot ds there? 0. 0. How about from E to A? 0. So that's the left side. This is the right side. Now, to get something similar to Kirchhoff's rule, we're going to move this to the left side and then see what we get. So we get that E minus IR minus L times DI dt is 0. So here is the rule that we discussed. You cross a battery, well, we didn't discuss this one, we done. You go from the minus end to the positive end of the battery, the potential will change by E. You cross a resistor in the direction of current, the change in potential is minus IR. Now here is the rule. When I move this to here, so mathematically we can view it the following way. You cross an inductor in the direction of current, the change will be minus L dI dt. So if you cross an inductor in the direction of current, the change is minus L dI dt. Okay. So
Did we not have a negative in front of the integral? So wouldn't it be negative E?
if we didn't have an integral, a minus here?
Yeah.
Yeah, so if we kept it this way, we would have minus E plus IR equals to minus L dI dt. And then it will, again, if you multiply everything by a minus sign, you come back to this again. Yeah. But I chose to multiply both sides by a minus sign so that it resembles this. Otherwise, it wouldn't be wrong. Okay, so, all right, we got to this. Let's eliminate the resistor now. Let's get rid of the resistor. Let's say I have just this, a battery and the inductor. In that case, I would have so E equal to L times DI. Okay. Why am I doing this? Well, we will need it, and I will need it now. I want to find the energy in the magnetic field. Now, how much work does the battery do when when the current gets through the battery? How much power does the battery get? Well, the power is I. The current through the battery times the potential difference across the battery. This is I. But this is L dI dt. E is L dI dt. Therefore, power is L I di dt. Now what's power? It's the work done by the battery, right? Where is that work going? To run a current into the inductor. Okay? To run a current into the inductor. So that energy would be stored in the inductor somehow. It would be in the magnetic field. We'll get an equation in a moment. So it will be stored in the inductor. That's the potential energy in the inductor. That's the energy stored in the inductor. So this power is the rate at which the potential energy is changing. increasing or maybe decreasing. So power is du dt. So du will be L times I di. We're going to integrate to find the total potential energy. So this is U. What's this? I squared over T. So 1/2 L times I squared. So that's the potential energy in an inductor. So if there is a current in an inductor, it has this much energy. It will have this much energy. And so let's watch it. Now I want to relate this to the magnetic field. So let's consider our solenoid again. For a solenoid, we'll have U equal to 1/2 L I squared. What's L for an inductor? For a solenoid? Yeah, it's I have it somewhere. This stuff, right? That's the U naught and little n pi r squared. And 1/2 U naught. Now what's capital N? Capital N is little n times L. Okay? Capital N. Okay. Little n is capital N over L, so little n times L is capital L. Capital N. Little n. So this one is little n times little n, so that's n squared, and then there's L, and that's pi r squared. More work. Well, 1/2. I have U naught n squared, I squared, and here I have r squared times L. And this resembles kind of the magnetic field. Magnetic field is U naught n I. So if I have mu naught squared n squared I squared, that's b squared, right? So let's make it into that. So what I would do is square the mu naught, but divide by mu naught. Okay? So mathematically it's identical. So now, what is this? U naught squared n squared I squared? That's b squared, right? Good. So I have b squared over 2 u naught. And now what is this? Pi r squared L. Geometrically, what does it represent? Volume. Yeah, that's the volume of the solenoid. Yeah. Right? The volume is cross-sectional area times height. So that's the volume. So let's define UB. It's the energy density. It will be the total energy divided by the volume. So you have a solenoid. That's a region where there is a magnetic field. And this is telling us whenever you have a magnetic field, there is energy density in the field. There is energy per unit of volume anywhere you have a magnetic field. This result, we got it for a solenoid, right? But it's general. So this is general. If you remember for the class we had yesterday, in the worksheet we skipped problems I think 4 and 6 because we didn't do magnetic energy. We're going to do it, we're going to use this for the toroid to figure out the inductance, that energy approach. So that's what we're going to do. The other class, just wait. So remember this. So compare this result to compared to the energy density in the electric field. What was it? UE. What was the energy density in the electric field? Yes? Huh? That was in a capacitor.
CV squared.
Q squared, let's think of E only, electric field. No Q, no C. Epsilon naught. That's the energy in an electric field, right? So notice both of them, you got E squared, here you have V squared. Epsilon naught goes with electric field, mu naught goes with the magnetic field. So, I'm trying to remember when we stopped to take the quiz. You sure?
No.
25.
25? 5 more minutes? Okay. Okay.
Thank you.
So, yeah, actually, I think it's probably a reasonable point to stop. I was going to do the circuit, but I would do it in probably discussion for each